Hello, today we're going to get into the formal theory behind the Sieve of Eratosthenes. So this will be for people into formal logic. We're going to extrapolate out and prove the Sieve of Eratosthenes. Instead of considering all primes up to 100, we're going to consider all primes up to a given integer a. Okay, and I'm going to propose that if I exclude all multiples, all composite multiples, I should say, of prime numbers up to and including the square root of a, leaving the primes themselves, but just excluding the composite multiples, then I exclude all composite numbers up to a, leaving only prime numbers up to a. So if I exclude all primes, if I take all primes up to 1,000 and I exclude the composite multiples of those primes, then I will exclude all composite numbers up to 1,000 squared, which is 1,000,000. Okay, proof. Well, we're going to start off proving that if I exclude all multiples of primes up to and including the square root of a, I exclude a if a is composite, okay, and leave a behind if a is prime. And then I'm going to extrapolate from there that that will work for all integers a lower than all integers lower than a. So we're going to consider cases of a such that we're going to consider a minus 1, a minus 2, a minus 3, and so we will then prove in the end that if we exclude the composite multiples of prime factors up to and including the square root of a, we exclude all composite numbers up to a. Well, let's start by proving the case for a. A can always be the product of two integers, period. For a natural number a, let's consider the case a greater than 1. So for a equals 2, a equals 3, a equals 4, a equals 5, proof. Okay, if a is prime, 1 times a. If a is composite, 1 times a. If a is composite and we have n prime factors for a, we could take these n prime factors and group them into two sets. Let's say I should use p instead of x, I know. But let's say I have n prime factors and I have the first, the third, the fifth. I could take all of the odd prime factors, put them in one set, and all of the even prime factors and put them in one set. If I multiply together all members of a set, I will have two integers such that those two integers equal a. And, it will work even for just 3 prime factors. I could take 1 and 2, put them in a set, leave the third one, or 1 and 3, put them in a set, leave the second one in another set, and then however I would do it. Okay, so bottom line is I will have integers c and b, or natural numbers c and b, such that c times b equals a. Maybe it's 1 times a, maybe it's some other way of arriving at a if a is composite. But in all cases of c and b, the geometric mean of c and b is the square root of a. Okay, now the geometric mean will be the square root of c times b, and for any c and b. And if c times b equals a, then that will always be the square root of a. Now the geometric mean will there are 3 possible cases. Remember that the geometric mean will be somewhere in between two unlike numbers. The nature of the geometric mean is such that if I have a lower number and a higher number, there is some y such that the lower number times y equals the geometric mean, and then the higher number divided by y equals the geometric mean. Or if they are the same number, then they will equal the geometric mean of the two. So, for instance, for 3 and 12, my geometric mean would be the square root of 3 times 12, which would be 6. It happens to be that 3 times 2 equals 6, and that 12 divided by 2 equals 6. Now, the geometric mean of 5 and 5 would be the square root of 5 times 5, which would just be 5. So my y would be 1 in that case. Obviously, 5 times 1 is 5. 5 divided by 1 is 5. So the geometric mean will always be between two unlike numbers, or if they are like numbers, then the geometric mean will be exactly that number. The geometric mean will never be lower than the lowest number or higher than the highest number. So in that respect, it's like the arithmetic mean, in that it will always be between the two numbers. Not exactly between, like the arithmetic mean, but somewhere between. Okay, so 3 cases. C is the lower number, B is the lower number, or C equals B. If C is the lower number, then C is less than the geometric mean. And remember, The square root of a is our geometric mean. We know that by simple substitution. So that's easy to figure out. Either c is lower than our geometric mean, b is lower than our geometric mean, or c equals b equals the geometric mean. Well, let's consider the first case. If c is lower than the geometric mean, meaning the square root of a, and c is prime, well, c times b equals a, so we know that a has a prime factor less than the square root of a. Now, if c is composite, at least one prime factor less than the square root of a, I should say. Okay, one known prime factor less than the square root of a. If c is composite, then, well, a has a number of prime factors less than the square root of a. Let's say b is our lower number, and case 2 is correct. B, we know that, well, c times b equals a. If b is prime, then we know that a has a prime factor less than the square root of a. At least one prime factor less than the square root of a. If b rather is composite, then there are a number of prime factors less than the square root of a. If c equals b equals the square root of a, then we have one of two possible cases. Either c equals b is prime, in which case our a has a prime factor. Actually, a would be the square of a prime that would exactly be the square root of a, which is fine because we set up to and including the square root of a. Or the number is composite, in which case a has prime factors less than the square root of a. But in all three cases, a has one or more prime factors less than or equal to the square root of a, unless a is prime, in which case it would be 1 times a. 1 would not be considered a prime factor. So if I excluded every single multiple, composite multiple of primes up to and including the square root of a, I've excluded a, because a would have to have prime factors within that set. Okay? So I now have demonstrated that one part of the Sieve of Eratosthenes, that if we exclude every single prime, the composite multiples of every single prime number up to and including the square root of a, we must exclude a if a is composite. A must have prime factors up to and including the square root of a if a is composite. So by excluding those, we've excluded a. Now, for numbers less than a, let's say we have a number less than a, an integer less than a, such that c times b equals our new number. Well, all of this would still be the case for our new value for a. C would be less than the square root of our new number, or b would be less than our square. And remember, these are any two integers, okay? Or b would be less than the square root of our new number, or c equals b equals the square root of our new number. Well, again, if c is prime, c would be less than the square root of our new number. It would also be less than the square root of our original a, okay? And then if c were a composite, its prime factors would also be less than the square root of our original a. Or let's say b is the lower number, the same thing, okay? The same rigmarole would go through. Our new number would still have prime factors less than the square root of that new number, which would also be less than the square root of our value for a. Or c equals b would equal the square root of our new number, in which case it would be still less than or equal to the square root of our original a. And that would be the case if our numbers less than a are composite. If our numbers less than a are prime, then by excluding the composite multiples of our primes up to the square root of a, well, would leave those alone because those would just be 1 times themselves. So this takes the formal theory for the Sieve of Eratosthenes and shows us that if we have every prime number up to a billion, and we exclude the composite multiples of those primes, we have excluded composite numbers up to a billion squared. We have generalized the case.